Okay, before introducing parity itself, I mention an important example of why parity is needed in quantum mechanics. And the example is that you have a time independent Schrodinger equation is a quite common case of hydrogen atom, and the first, you can say, case of solving time independent Schrodinger equation can be that if the potential energy is zero, that is called free particle. In the free particle case, mathematics would say that your solution, wave function, can be exponential, namely e power iota kx or e power minus iota kx, or even odd. Even means cos kx, and odd means sin kx. So you have to choose one set, and the choice is not random. There are reasons behind it. So that reasons, what are the reasons, how we make a choice, that's the problem I'm mentioning. That this is a need where parity is needed. This is a problem where parity is needed. Okay, I don't remain limited to that trivial case of potential energy zero. In the middle portion, I go to a more general case that potential energy is even. It can be non-zero under space inversion. Zero is an example of that. Zero doesn't change if you take position reverse. But in general, if it is non-zero, still it doesn't change if you take R2 minus R in position, your reverse position. Then I have calculation etc. to convey you the result in a variety of ways. That in that case, if wave function must be even or odd, like even is, for example, cos or sine, and these cos or sine or even or odd are eigenfunctions of parity. So that's how I use the word parity toward the end rather than toward the start. But anyway, before completing, I have to introduce parity as well. So let's apply that scheme. So the first thing I said, I tell you what I said about time independent Schrodinger equation. Now, and in that case, I mentioned V is equal to 0, and a V is equal to 0 is a particular kind of potential energy. That means a particular case. So now I've used the word case, and first I define the word case in context of Newton's second law, classical mechanics. Case is F is equal to ma. If you take a variety of expression for force, you have a variety of cases. Try to learn this word. If you have F is equal to mg, that's one case. If you have F is equal to Hooke's law, it will be minus kx, second case, and so on. Now coming to quantum mechanics, and a quite common example of quantum mechanics is solving Schrodinger equation. And Schrodinger equation, you do not have force, but you have potential energy. So the case means a particular expression for potential energy, and the simplest case could be that potential energy is zero. If potential energy is zero, in that case, first we write Schrodinger equation, and the question is which of the two equations, time dependent or time independent. But the answer is that since potential energy is zero, so that is independent of time. So Schrodinger equation is also independent of time independent. So that's the time independent Schrodinger equation. That is there. You can say kinetic energy operator plus potential energy is 0, h, this becomes h psi equal to E psi. Now the rest is the mathematics. In mathematics, you first convert to, you can say, standard form, second derivative, and the rest of it, take it there, and you define that thing to be minus k square. If E is positive, minus k square becomes negative. I kept it separate. So k square is positive. So now think of that. You compare extreme left to extreme right. You have to think of either you do standard mathematics, or in this case you can even think, and then whatever you think you substitute and verify. You think of a function who you twice differentiate, that doesn't change. What it can be, what your mathematics knowledge says. It can be e power iota exponential, and since the second order differential equation, so you have to take 2 e power iota kx minus kx. You just check it. You put this in that, you verify. You put this and that, you verify. Or second derivative case, twice differentiation keeps even sine or cos unchanged as well. So you can have sine or cos. So you have 4 solutions, but since equation is second order, so you cannot take 4 simultaneously. You have to choose either this set or that set. So the question is which of the 2 sets we have to choose. So and that is this topic of this lecture. That amongst other things, parity helps you choosing between these 2 sets. So furthermore, I just point out characteristic of these 2 sets. The first set, exponential, each member e by iota kx, when you pay x2 minus x, it changes drastically. So it's not proportional to original. And similar about the x e by minus kx. So they have no symmetry under x2 minus x. But the second one, x2 minus x, that's an odd. It remains unchanged, just extra minus sign, and that is even simpler. It doesn't change. So the second set is even or odd. And now the thing is, if potential energy does not change under space inversion, then what do you expect? The whole plan is you build an expectation or guess, and then we see if actual mathematics verifies this or not. So your guess is the following. Guess starts with realizing that in the solution of Schrodinger equation are effects of potential energy. Okay. In that, what the case to case varies is in Schrodinger equation is potential energy. So if a particular kind of potential energy, you have particular effects. Effects means solution of Schrodinger equation, namely wave function and eigenvalue. These are effects. Now, if potential energy is of a particular kind, that means it is even under space inversion. Your effects will also be of that kind. Effect means physical prediction. Will not change under space inversion. So that is we expect. And now, before actual taking calculation, I write these expectations in mathematical symbols, and these are there. That if potential energy is even, you can have this shape, left or right is same. In 3 dimension you can say, sorry, it's a typo error here. It's a V of minus R is equal to V of R. It should be a plus here. So in that case, under R2 minus R, potential energy does not change, and its effect means one effect could be probability density, and that also doesn't change. So that means if you change R2 minus R, probability density, which is wave function squared, doesn't change. So if it doesn't change, we expect that it could be either unchanged wave function, or if it's a minus, then even then square doesn't change. So these are our expectations. In the rest of the slide we have to see, are these expectations fulfilled or not? And the answer is that these are fulfilled, and I have to justify that claim. And during the process of justification, we have to learn this word parity. Actually, it's not during, it's before. Before justification, first I define parity. And the definition is the following. By that time maybe you have picked up what I'm calling parity. I have spoken the phrase space inversion. That's it. That's a parity. Okay? So that means space inversion means R becomes a minus R. You can have that either in R cat or in wave function. Wave vector or wave function. In both cases, if R, you change R to minus R, that's space inversion and that is parity. So the way I have written it, it looks like there are two independent definitions. Actually, they are not independent. Assuming first, we can derive the second. But I think, and the proof is, I think, this bit involved. So if I start prove here, you might be lost. You might not keep your attention to the main topics we have addressed. So that's why this proof I have postponed to the last slide, and before that we continue. Actually, in that I will use only the second one, and then I continue to do the following. The following means I have to define eigenvalues and eigenfunctions of parity. You remember before I have defined position operator and momentum operator. Now position momentum operator are defined by their eigenvalues. So the eigenvalues are known first and the operator comes second. For example, momentum, it's a definition of momentum that is eigenvalue is classical momentum and so on. So the eigenvalue is nothing new and you already knew it even before defining. But in case of parity is purely quantum mechanical operator. That in that case, first the operator is defined and eigenvalue has to be calculated. How to calculate? That's the question. Answer is, so to calculate, what you should do is, basic idea is that is parity space inversion, and if you invert an inversion, you understand? If you do it twice, and first you R to minus R, and then again minus R become original. So parity square is unchanged operator. This means identity. Now that thing you write that in actual mathematics in two forms. One using the definition of eigenvalue, and then repeat calculation with using definition of parity, and then compare answers. So that's the whole plan. So now I start details. As I said, twice use the definition, twice used parity again. This is twice parity. And first I use the definition of eigenvalue. Operator act on function give you eigenvalue and function. Eigenvalue I have called lambda. Now by color, what I mean to say, the red apply here and red applies here as well. Red applied here is that, and red apply here is that. Now left hand side is just nothing special, just write p square. The main thing, I hope that right hand side is also simple. And right hand side, all you do, what you have done with what you have done with blue, do that with red as well. That means in blue, p was replaced with lambda. So if p will replace with lambda, there is already lambda square equation, and that is equation 1. And you write it, and now you do, in a way, repeat something different I was saying, or whatever you call it. You do the same, but this time use definition of parity, not definition of eigenvalue. Otherwise, repeat. So left hand side is nothing new, and right hand side, P operates on that. You know what happens? Now it's a crucial in that proof. If you have, in the first case, in the first application of operator, if you have used definition of eigenvalue, in the second you use definition of eigenvalue. Do not mix. And if in the first application you have used definition of parity, then in the second also use definition of parity, and parity would become minus R to plus R, and that's it, and that's minus R to minus R. So become minus of minus r become plus r. That's equation 2. Now you compare equation 1 and 2. Left hand sides are same, so right hand sides are also same. So lambda square psi is equal to psi. Since psi is arbitrary, that means lambda square is 1, and that means either lambda is plus 1 or minus 1. So we have found eigenvalues. The next topic is eigenfunction, and in that case, as usual in even matrices, you say ax equal to lambda x. You find lambda, and then you put lambda in original equation. So that's what you do. We have found lambda is equal to plus 1, that we put in original equation, and original equation is that. You see, it's is there. Here I have written it again, and for some purpose I have colored it blue. Otherwise nothing new, it's same. Just put lambda is equal to plus 1 right hand side. It's a simple. Left hand side, what you do is you use the definition of parity. That will become psi of r becomes the psi of minus r, and here I have already spoken psi plus r. Now do you recognize what is that? This is a definition of an even function. So the conclusion is that with lambda eigenvalue plus 1 of parity, eigenfunctions are even function. You cannot derive any actual expression. All you can say is an even function. And if it is minus 1, everything is same. I don't spend time on it here. Only here minus 1 is there, and you recognize this is an odd function. So I find eigenvalues and eigenfunctions of parity. So apparently I have started and you may so much say even unrelated topic, but I tell you it's related. At least the word has some continuity. I ended the previous slide with the word even function and that odd function. And related, at least the word is same, usage is different. Now this time you don't have even function, you have even operator. So if you ask me what is even operator, I think it suffices to say that even operator commutes with parity. And if the word commute is new to you, learn it. It's a very crucial word, used again and again in quantum mechanics. So commute means you change the order of operation, you interchange, and the result doesn't change. So if there is an operator in such a way that you first apply parity and then operator, or you first apply operator then parity, the result doesn't change. If that is followed, then operator is even operator. That's the definition. Try to remember. And if it is too much abstract to you, then I make somewhat concrete, somewhat familiar by giving an example. An example is, I think, like maybe you are expecting it. Anything square would be even, but anyway, particularly I justify it for p square. Divide by 2m become kinetic energy. And because the parity operates, I said it, I will use only that definition of parity which operates on wave function, position wave function. If momentum, you have to say some attention to that. This is parity, which is not boldface, and which is boldface is momentum. In position, with position wave function, momentum becomes minus iota by d by dx. Constant doesn't matter to my message, so I just say that is proportional to second derivative. So the question becomes, is second derivative even function or not? And the answer is yes. And to justify the answer, what I've done is I have calculated left hand side here and right hand side in the next line. So the left hand side is what? Left hand side of this equation is first to apply parity and then operator. Operator is second derivative. So here all I have done is only in the black portion. I have applied parity, x become minus x. Blue portion unchanged, nothing. Now go to right hand side. On psi, because it's a derivative, it has to operate on something, so I had to introduce psi. Otherwise it's a second derivative and then parity. Here you have to do some more application of parity. Before that I used parity in such a situation that the position was occurring only once, so that I reversed it. But even if position occurs twice, or in this case twice, maybe third or more, but not third here, second twice, wherever is x, you reverse it, and then you can, hopefully you can see that I've all, and that's it, nothing more. X minus x, that is also minus x, and the result you can see that is a minus, so it becomes minus square, so it is the same thing, it becomes same as that, minus square becomes plus 1. So that means the left hand side answer is same as right hand side answer. That means second derivative is even operator. And also, because of equation 2, you can say if second derivative is even operator, kinetic energy is even operator. And that is crucial for us, because kinetic energy is first term in Hamiltonian, and the way lecture started, our target was Hamiltonian, time independent Schrodinger equation. So in that we have learned an important property of first term, namely kinetic energy term in time independent Schrodinger equation. That we have learned that is an even operator. The question is what? So what if it is even then and then I have gained some general mathematics. You might feel that I'm introducing scattered topics, but the thing is, relation to the previous is that even operator commutes with that. So, but rather than going to Hamiltonian and parity and so on, first I'm doing a general mathematics, that if two operators commute, it may be even operator or maybe Hamiltonian or parity or whatever, first do a general mathematics. That has its own usage. This theorem is used for other purposes as well in this theorem. So with patience you spend some time on that as well. And then I come back to these applications I was talking about before. So for the moment you just learn mathematics. As it were, they can be any. Only thing you know is they commute. And A has no non-degenerate eigenvalue. If that is the case, then eigenvector of A are also eigenvector of B. Non-degenerate, if you have forgotten what is the definition, I remind the definition as I use it. Now just do not be stopped by that and just continue reading the proof. In proof, what I have done is this is just I have written the definition of eigenvalue and eigenvector for A operator, and then apply on both sides by B, and the red color means, as I have done it before, red will apply here and red has apply here. On the left hand side, meanwhile, I have done some change. You didn't know what it is. BA was making AB. Why? Because they commute, and a commute means AB is equal to BA. And now think of right hand side, B means, now equation 1 and 2, how do you compare these two? Equation 1 says that with eigenvalue an, eigenvector is psi n. And equation 2 says that for eigenvalue an, can you see any eigenvector in equation 2? Think of that as I go to show the next line. Have you thought? In equation 2 as well, something is appearing in left hand side as well as right hand side. That means something is eigenvector. And now what is that? This time it's a composite thing, but maybe, hopefully you are not confused and you are understanding enough that whatever it is, if it appears left and right, that's eigenvector. So that means apparently you would say there are two eigenvectors of A for the same eigenvalue an, but there are two eigenvectors. First in equation 1 and the second this composite one. But for one eigenvalue there are two, apparently two, but now I remind the meaning of non-degenerate, even if you have forgotten or even if it is new to you. Non-degenerate means that for y eigenvalue you can only one eigenvector. If they look twice to you, then no, they're not two, because this is non-degenerate, they are one. There's only one. If there are only one, means if they look two, they are actually one. That means all in all, is just convert that to English to mathematics. That means they are equal. And that becomes the equation. And once you have written that equation, you see what's the meaning. You compare equation 1 and 3. So, yeah. Can you see the proof here of the theorem? What is eigenvector of A is also, here it's appearing as eigenvector of B. So, that's it. So, that theorem is proved. Okay, before going to the next slide, must clarify one thing, but possible confusion. That equation 3, in place of eigenvalue, you have 1. But I must point out that 1 is an example. It was not necessarily 1. It could be, you can say arbitrary. But I can choose it something particular. Now, first I say, why did I say arbitrary? Here it could be something arbitrary. And the justification is the following. Justification is that you remember, you try to note where this psi n came from. Psi n came from equation 1. And equation 1, if I multiply both sides with say 3, hopefully you can see equation 1 remains unchanged. I multiply with 5, unchanged. I multiply both sides with -7, unchanged. But I use this freedom to multiply both sides with Bn, B subscript n. I tell you why this particular name I have chosen. But you just do it. So that means whatever you had psi n, it can be replaced with Bn psi n. So in equation 3, psi n can be with Bn psi n. So that means eigenvalue can be Bn. And once you have written, you generalize equation 3 with Bn, and now hopefully you can see why did I choose this symbol Bn. I mean, I've been speaking about 2, -3, -7 and so on, but I wrote my Bn. You know, the name is suggestive. Once you have written, you can see Bn is what? Bn is eigenvalue of operator B. All in all, a theorem and then comment, so the next net result is that under this, if this condition is fulfilled, and that's normally fulfilled, that's not much spoken about that. Main thing is if the two operators commute, then eigenvector of A are also eigenvector of B, but eigenvalue can be different. There's no restriction on eigenvalue. They can be anything. That this theorem doesn't tell about eigenvalue. This tells only about eigenvectors. Okay, let's see what is next. And the next is, if two operators commute. Okay, this is not, in this slide I don't have any new result. I have rephrased it, I have rewritten the conclusion of the previous slide in some other terminology as well, which is also used. I mean, the result is so important that it appears in a variety of ways, and because this variety is spoken about, so you should know that variety. Otherwise, if you understand, there is no new result in this slide. The result was in previous slide, but the terminology is new. And the new is that if, the result is that if A and B commute under certain condition, eigenvectors of A are also eigenvectors of B. Now, learn what this result means. If there are eigenvectors of A, there is an eigenvalue of An, then that means A can be measured, and the physical prediction for measurement would be An. And An is one number. Okay. And then B has also same eigenvector. That means B also has eigenvalue, and we have a prediction what is the result of measurement, that will be B. So the crucial thing out of these two things, that if A can be measured, B can also be measured. Rest details you can read, or I already spoken, but pay attention to that. If A can be measured, B can also be measured. Now this means if A is measured, you remember I spoke A is something like value, for example, is a 4. If it is a 4, then what is uncertainty in 4? There's no, it's not 1, 4. There's uncertainty in A is 0. And B has also some eigenvalue, maybe you can say 9. So what is the uncertainty in 9? There's only fixed one certain number. So uncertainty is 0 for B as well. So both uncertainties are 0 and the product is 0. And you may think that you may recall that in Heisenberg uncertainty principle, if you have a delta x, delta b, that is iota h bar, that's a non-zero. So you think it clashes with that? And the answer is not. This result is not claimed to be general. This result is claimed to be the case only if A and B commute. In Heisenberg uncertainty principle, you have position and momentum, and they do not commute. And the proof of that statement is later in the course. But anyway, here is just a clarification that if they do not commute, then this result doesn't apply. So Heisenberg uncertainty principle is not any contradiction to that. So just this result is what you should learn without feeling that it has any contradiction with anything else in quantum mechanics. Anyway, maybe more on that. Now coming to the main task, main topic I started this lecture about time independent Schrodinger equation and its solution. I said about free particle, and then I became more general. Any even potential energy. If potential energy is even, kinetic energy I've already told you is even. That's slide number 6, 3 slides ago. I mean, there I said second derivative, but then I said second derivative is even operator means kinetic energy is even. So if kinetic energy is even, then potential energy is also even. That means then kinetic energy plus potential energy, namely Hamiltonian, is even operator. And there I told you in the same slide 6 that even operator commutes with parity. And then before that I said these two operators commute, then what happens? I think not two slides, that was slide 7. That if they commute, then eigenfunction of one are also eigenfunction of other. So one was Hamiltonian, the other was parity. So that means that the particular application we got here is that if potential energy is even, then the usual wave function, namely solutions of Schrodinger equation, they are also eigenfunction of parity. And eigenfunction of parity are what? That I had in slide 5. That means they are either even or odd. And I show you the picture, an example. Even could be this, same left, same right, and odd could be reverse. I tell you later what is the origin of these pictures. And before that, before going to the next slide, I just tell you that this is not only the result of previous slide, but also something we had guessed in slide number 3. That if potential energy is of that kind, our physical prediction will also be, psi square will also be of that kind, and the psi would be even or odd. So that I've already spoken as expectation or guess, and that all that guess has turned out to be true. Now, in a way, you can say this lecture is over, and now you have 2 more slides and then conclusion. And the topics in these slides are, the next you have a half optional. And the next to that is full optional. Now this slide I'm going half optional. You know, half means the heading you must remember. That's crucial. The position, momentum and parity are Hermitian operator. I don't have time to give you detailed proof in any video, but this is you can read any standard text of quantum mechanics to read proofs. For me, the more needed is that you remember this result, and the way, one possible way to at least to talk about the result for a few minutes so that it is settled in your memory. One way could be to do something which is in itself a bit optional, but that can help you memorize the result. And the result means parity is Hermitian operator. To spend some time on that could be that we know some theorems about Hermitian operator, and one of the theorem is that eigenvalues of Hermitian operator are real. You apply that to parity, eigenvalues of parity are +1 or -1, both are real. So you have spent some time on parity Hermitian relationship. Another theorem says that eigenvectors of Hamiltonian operator belonging to different eigenvalues are orthogonal. And now you again repeat that parity is Hermitian operator. So what I've just spoken about Hermitian operator applies to parity to give you sentence that eigenvectors of parity belong to different eigenvalues are orthogonal. Now parity has only two eigenvalues, +1 or -1. So hopefully the names are suggestive that eigenvalues of parity belong, eigenvector of parity, sorry, the word is eigenvector. Eigenvector of parity belong to +1 is, I have named plus cat, and with -1 is a minus cat, and they are orthogonal. And that's a claim, and I prove it. And for proof is just is a simple one line. Bracket, orthogonal means that dot product is 0, and dot product is a bracket. Now bracket is because I have defined parity through eigenfunctions. So cats I have to convert to eigenfunctions, position eigenfunctions, and that topic is called position representation. And position representation has 4 things, and these are: the first is that bracket becomes integral, position integral. Cat becomes a function. I have given a subscript, is just a name. And bra becomes complex conjugated. So you use that, and then psi plus is wave function corresponding to eigenvalue +1, and that I've told you that that's an even function. And this minus is odd function. You have to calculate integral. You don't need actual calculation. I didn't give you any formula, so you might be thinking, how is it possible to calculate it? And the answer is, it's an odd function multiplied even function. The product is odd function. The odd function has a particular characteristic. Should I remind you, or you can guess yourself, even now? Anyway, whatever it is, I tell you. If it is odd, and the limits of integration are symmetrical, so as much is to the left of 0 as is to the right of 0. To the left you have a negative area, to the right you have positive area, because that's what odd means. So the net area is 0. So this is integral. Anyway, coming back to physics of it, that means they are orthogonal, and we have verified a theorem for Hermitian operator for parity. Main thing I need is that you remember that parity is Hermitian operator, and you remember the position momentum are also Hermitian operator. So that's the main thing needed. So before finishing, I have some time on an optional topic, and that is that in this lecture I showed you 2 definitions of parity, and I've made use of only that definition. But the first one which I wrote is not unrelated, but it is related, and maybe very much related, in that you can start from first and you can prove the second one which I've used. This is a claim, and justification is the following. First you use that result which I have written many times, but even if it is new, you can say this is at least plausible to you, even if it is new. That means you take any vector and you multiply with basis vector, and the result is component. Ordinary vector v, you multiply with I unit vector, you get vx. But here the label is not I, j or only twice, the label is r, which is uniform, but so the component becomes a function. So that's the result. You take Hermitian conjugate of both sides, and Hermitian conjugate has transpose and complex conjugate, and left hand side will happen. It's just number, so there's no transpose, only complex conjugate. Right hand side, if you take Hermitian conjugate dagger, that cat becomes bra and bra becomes cat. That's it. I continue. Next I applied both parity on both sides, parity operator. Now left hand side is just what I've spoken, I've written mathematics. The actual operation starts on right hand side. I apply parity on right hand side, and right hand side you have r cat, and starting assumption has been, which I've colored red, that parity operates on r cat gives you minus r. So parity operates on r cat gives you, parity operates on r cat gives you minus r. So the bra I have colored blue for some reason, which should be next, and these reasons are there. They start with saying that any vector can be written as a linear combination of basis vector. For ordinary vector you have v, it can be written as a linear combination of I unit vector, j unit vector, but in this case you don't have I and j, you have a continuously varying r. And in component you don't have Vx, Vy, you have continuously varying wave function. Otherwise it's just usual result, even if it is new to you, although it's not new to those who have watched previous lectures. But even if it is new, you can say it's a plausible. And you take a Hermitian conjugate of both sides. This means cat becomes like here, cat becomes Hermitian conjugate, cat became bra, cat became bra. And the right hand side you have a psi dagger, the transpose is not applied here, it's only compressed conjugation. And here on cat becomes bra. So now you have rather detailed lengthier expression, but whatever it is you put in equation 1. And equation 1 has also left hand side that I have shown you before any change, without any change, and right hand side I have substituted that. And now you do mathematics on that. This is same, D3R is also same, I have only changed color, and the dot product is of r and minus r. What I say, dot product is bracket, and bracket is Dirac delta. And now with integral, Dirac delta has integral is calculated through shifting property, and the shifting property means integral is finished. So when it's finished, that means r is finished and is shifted to where that is 0, namely when r is minus r. So r is shifted to minus r. That was the mathematics. And now concentrate on the result, the extreme left to extreme right. Is that what we had to prove? Quite, but there is some difference. You had p, but psi star, and we have to prove psi. So to convert psi star to psi, what I do is I take Hermitian conjugate of both sides. Rather than conjugate, I said Hermitian conjugate. That was to tell you, if it is Hermitian conjugate, then I know what is p dagger. If it is p star, I didn't know what is p hat star. So it is p dagger. We know p dagger is p because p is Hermitian. So you know that. The rest is here is the dagger is simple. Is just convert compressed conjugate to ordinary, and now your result is that what we have to prove. So as I said, this is you could say this was an optional topic, and now I conclude and then finish. So what we have learned. Now in conclusion, I can start with parity definition, because now we have learned, and the definition is the parity is a space inversion operator. That's the first lesson we learned. And then the second lesson is that its eigenvalues are plus 1 and minus 1, and eigenfunction are even odd function. That's the second lesson we learned. The third lesson we learned, and there it looked like scattered topics, but I just write together, and the comparison will help you seeing a structure. A result we proved was that an even operator commutes with parity, and then we also said that if two operators commute, they have common eigenvalues, common eigenvectors, and then toward the end I applied to our original case. Operators we need are Hamiltonian and parity. About Hamiltonian I said if potential energy is even, kinetic energy is already even, so Hamiltonian is even. And then if it is even, then eigenfunctions of Hamiltonian, which is usual wave function, they are also a common eigenvector with parity. That means they are eigenfunctions of parity as well. And you remember what are eigenfunctions of parity, namely even or odd function. And the thing I started with lecture, that even has an example of cos and odd an example of sine. So that's all. So thank you for watching, and don't forget to subscribe to this channel. So